The goal of this video is to simulate a projectile with and without drag. We'll create the projectile first, launch it, then we'll write a script to launch the projectile with a different speed, make some plots, and record the animation. Once CoppeliaSim is open, go to Add, Primitive Shape, Sphere. The size looks okay. If you want to change the color, click on color. Then say it's white, so just go RGB as 0. Okay. It's a good idea to save. So save the scene as projectile. Okay. Now to make this work, what we'll do is we'll move the sphere slightly up. So we select the sphere, we click on this translation key. Okay. Here you see it can move in the X, Y direction. We only want to move in the Z direction. So we check the Z, uncheck X and Y. And now when you move this, it can actually move it in the Z direction. So let's set it up here, zoom out a little bit. Okay, and then to run the animation, we click on this. So you can see that it fell down, doesn't quite look realistic. That's because we have not done rendering equal to the real-time rendering. So click on toggle real-time and play this. This basically shows how it would move in real time. So that's a projectile with no drag. Okay, now in order to set a speed and to do interesting things with it, we'll write a script. So for that, first you need to go to add associated child script, non-threaded Python. I'll do that. And then once you do that, what you'll see is magically in your sphere, sort of a notepad will appear. You can double click this and what will open up is a script. Okay, let's do that. I go to, first I need to click sphere, right click, add, associated child script, non-threaded, I'll go for Python. Okay. And then if you double click this script here, you will see the child script which looks like this. Okay. Now, once this is open, when you say run, it works all fine. With the first time when you do this, it'll actually not run fine. That's because you have not told CoppeliaSim what the Python path is. So when you say click run, if the script fails, it'll basically show some kind of a red. There will be all red items here, arguments saying that you've not set the path. If that happens, then what I've done here is I've provided you some information on how to set up the Python path in CoppeliaSim. So when you click on run, it'll actually run the same simulation without any problem. Okay. Now that we have it running here on my end, let's see how to, we know how to access the script, but let's see what the script does. Here is the 4 functions in the default script. Note that it says Python, it means Python, we are writing a Python script. The initialization is to initialize numbers. This part of the function is called once. The actuation and sensing are 2 functions which are called continuously in the loop. Okay, and the cleanup is something which you'll never really use, but before you close the program, you want to delete some things, variables. That's what is the cleanup for. Okay, let me illustrate the init actuation sensing, what they do by just printing out simple. This is where the messages are printed. I'll open the script. Okay, so I'm just going to say print init. Okay, so if I run this now, what you see is that it ran the simulation, but also printed init here just once. That's because this part is called only once. Let's stop this. Print actuation. And now if you run this, then you see that it continuously prints actuation, indicating that actuation is called all the time. If you also say print sensing, and you run this now, you'll see that it actually stop this. It actually prints sensing actuation, sensing actuation. That means that first or first sensing is called an actuation called, or vice versa, but it just keeps calling this in a continuous loop. So that's useful in future when you have to write code. Okay, now that we have this, first let's see how we can set the initial velocity of the sphere. Just like some other softwares, what you need to do is we need to first create a handle for the sphere. What that means is we create an object for the sphere by using this thing called sim.get object. Okay, what I have here is a sphere. I took it right from here. The sphere, the way it is written here, if S is small, it should be small. This is the name which I can give it. I can specify whatever name I want. How did I get this? I'll come to that in just a bit. Okay, this is just creating an object handle for sphere, which I can now use. Now I want to set the initial velocity. Okay, so I actually have the link which basically will tell you how to get these API functions. I'll click this and go from there. But today's video, I'll be basically using the object float param to set the initial conditions. I will then use get object position, get velocity to get the position velocity of the sphere. I will then use add drag force, add force in torque to add drag force, and then I'll show you how to use a graphing tool to graph the position and then finally recording the simulation. Okay, so let's click on this. Okay, if you click on that link, you come to this regular API functions. Okay, so for example, get object is over here, and it basically, if you click on that, it gives you various synopsis: C, Lua, Python. So Python, you want the object handle, then you say sim.get object handle, then you give the object path, which is that / sphere. Okay. Now in this case, what I want to do is I want to use something called set object float param. Set object float param is a function which is used to set up various parameters. Okay, so the way it works is you give the object handle, so in this case it will be sphere. There's a parameter ID associated with the initial velocity, which I'll show you in just a bit, and then we give the value for that. So if you want to set the x velocity and you want the velocity to be 1 meters per second, you put that parameter, which I'll show you, and then the number 1. Okay, so let's see how to get the parameter ID. So actually, if you go back and scroll all the way up to this same link, you'll see object parameter IDs, and we need to search for init velocity. So you can see it's init velocity. We need this one. Okay, so init velocity x, init velocity y, init velocity z. So let's go back and use that. Okay, so sim.set object float param. That's the function. It also tells you how to use it. So object handle is sphere. The parameter ID was sim.shape float param underscore init velocity. That's the one I just showed you. And then I need to give it some underscore x and a value of, let's say, 1 meters per second. Okay, so let's see what's the effect of this. Now, if I launch the projectile, you see that it's not only falls down, but moves in forward. That's because of this 1 meters per second. Okay. I'm also going to set the z velocity, and I'll keep the problem plane. I'll keep the sphere planar, so I won't set a y velocity, only an x and a z velocity. So let's set the z velocity to be an upward velocity. So let's say 5. Okay, now, if I run this, see that it jumped up and went down. We can zoom out a little bit and watch it better. Okay, so that seems like it's working. Okay, now let's see how to access the velocity. Okay, for that, we go back to the API and see if there is a velocity variable. So this is for joints. I'm not into joints yet. What I need is for shapes. So this is the one I want for shapes. So set sim.getVelocity. So this is the synopsis of getVelocity. So I can just copy this. Okay, and here I will try to access the velocity in the actuation. I want to access it every time the simulation runs. So I'll put it here. Now, this is saying that the input is a shape handle, which I think was the sphere, and the output is a list. So it'll have velocities in x, y, z. So I don't quite need the list. Okay. That should work. Now, if I run this, this will not run. It actually gives an error, and we can look at the error and see what the issue is. So here you see it says name sphere is not defined. Sphere was defined in this function, and actuation function doesn't have access to it in over here. So what we do here is just say global sphere. Okay. Now if you run this, it works just fine, but it's not printed the velocity. So to print the velocity, this is what I typically do. I just copy paste my code. So I say Vx equals, I concatenate the strings, linear velocity in x, that's index 0. I can do the same thing for Vz. So x, y, z, so z is index 2. And now when I run this, you can see it actually prints the velocity in x and y. Now, the purpose of doing all this is for me to add a drag force proportional to the velocity. So my model for the drag force is fx, okay, will be minus some constant times Vx times square root Vx square plus. So square is written as this way, Vy plus Vz, okay, and so on. Okay. Now to write this, I need to define C. It's just a constant. I'm just going to put some value, 125. Okay. Vx is nothing but linear velocity in x. Vy is linear velocity in y1, and Vz linear velocity 2. Okay. I also need V. I'll call this whole thing as V. So V equals I need to use math, so I'll import, and so I can use math.square root. So once I have that, all I need to do now is write fx as minus c times vx times v, and I can do that for y. Okay. And z. Okay, now I have created the forces, but I need to apply them to the body. So what I do is I try to figure out how I can do that using the API. So I need to add force to a shape. So I need to go all the way to shape. Shape is right here. So I have two options, add force and torque. Let's look at both of them. Let's look at sim add force. If I want to use sim add force, it says it's a non-central force to a shape that is dynamically animal. A non-central force is a force which acts at a distance from the center of mass. So for that, I need to specify the shape handle, the position, and the force. Now I could use this by specifying position as 0, 0, 0, which means that it's applied at the center. But what I'll do instead is I'll actually use force and torque, which is looks something like this. The good thing about this is it applies force are applied the center of mass, so I don't have to really work with position. So I need to specify force, I need to specify torque. In this case, the torque at the center of mass is simply 0. So let's take this back here. Sim add force torque. The shape is sphere. I need to create a force array, x, fy, fz. I need to create a torque array, it will simply be 0. And so this is force, this is torque. Okay, and then let's run this. Okay, so there's a difference. If you put this as 0, which means there's no drag, you see it jumps high up and it goes beyond the screen and comes down. But the moment I enable the drag force, it actually goes much lower. And then, okay, so this is how you can add a force. Okay, now let's go to the step of printing the positions. So again, we go to the API and see under shapes if there is something to print positions. Okay, maybe I should just search for position. This is joint position. That's not what I want. Yeah, this is for any scene objects, not specifically to shapes, but it works. So let's just use set object position. Okay, scene object, I need to do get object position. So get object position is something like this. You need to give the handle and I need to give relative to object handle. Now you can get the position with respect to the world. You can get the position with respect to another body. So in this case, we only want position with respect to the world. So for that, the relative to object to handle is usually -1. Let's take this and paste it here. It's position. The handle is here. And then as I said, this will be -1. -1 means relative to the world. Now, if I want to print it, I'll just copy the strings. I need the X and Z position. X, Z. Replace this with position. And then run this. So it's printing. You stop this, it's printing VX, VZ, XZ position, and so on. Okay, now let's get to the point of graphing this position. So I'll make a plot of X and Z versus time. So for that, what I'll do is I'll use, there is graphing. So I need to add a graph stream and then I need to set the graph stream value. So I need to initialize the graph stream and then I need to then set the X to that stream value. So I'll show you how this is done. First, before I do all that, I need to do something in the scene. I need to add a graph. Note that the name of the graph is graph with a capital G. I'll get an object for the graph. So graph equals sim.get object graph. I'll make it global. Okay, once I've done that, what I'll do next is I'll add a graph stream. So let's see what the syntax is. Add graph stream. This is the syntax. The graph handle, that will be graph. The name of it. So X and Z. I'm using position of X and Z. So maybe position, pose X, pose Z. The units, meters. Options, you can just ignore that. The color would be RGB value. So 100 would be red. So let's take this and put it here. So I'll walk through this. I need to give it a name. So graph X, add graph. The handle is for graph. I need to give it a name. Suppose X. I need to give it a unit. Meters. Options, you can just put 0 for now. Color, we can just put 100. And you can just ignore this last one. It's by default will be 0. We can do the same thing for a Y or Z, sorry. So graph Z, this will be pose Z. Let's put a value, well, let me make it blue. RGB is this one. And I will be using this later on. So I'll just make a global variable for this. Global graph X, global graph C. Okay, now once I have this initialized, I need to set this to the position. Okay, that's the final step. So what I'll do is I'll go here where I already have collected the position, and I'll use uh, a function called graph value. So if you go here back, the graph, you can say graph stream value. This one basically, you take the graph handle, the graph x or graph z. You would then, sorry, you need to take the, it will be graph. The stream ID would be your graph x and graph z, and then you'll put whatever value you wanted to put there. So let's take this, go here. Graph handle is going to be graph. Stream ID would be the one I wrote earlier, graph x. The value would be position 0. You can do the same thing for z. Okay. Now when I run this, you'll see that it produces the x and z plot versus time. So let's run this. So red and blue. Okay, now that we've got the graph, the final step is you might want to record this and share it. So for that, what you can do is the following. You can go to the recording utility here. You can select a location. I like to put it on the desktop. Choose. And what you can do is you can say launch at next simulation start. It'll, if you want to show the cursor, I would rather not show the cursor. If you want to hide the information, you can hide it. And then I typically like to go for the last option, MPEG, MP4. Okay. So once with that, you can just say play, and it is recording now, and you can say stop. It'll say recording saved. So if you want to take a look at the recording, you need to go to the desktop and view it. I'm going to find it on my desktop. Okay, so that's ends the video.